coming through at all the sites. So again, my apologies for the error there. So a little, or the outline, I do want to spend a little bit of time giving you a background on visualization, because if you understand visualization in general, you'll be able to move, very smoothly or with minimal effort between the various packages that you might be needing to use. And in some cases, as we'll talk about, if you're working in a particular domain, there's particular packages that the scientists are used to working with. But if you understand the visualization at a more abstract level, that will help you actually make those transitions and scale your data. So I do want to spend a little time with that. Then talk about ParaView, again, looking a little bit at its architecture so you understand what goes on when you need to scale it up into a distributed mode. Look at a couple of different examples that we've done here at IU with different data types. Talk very briefly about the advanced features. So the title's a bit of a misnomer because we won't spend a lot of time demonstrating those advanced features because if you don't do the basic things and get these tools working on your desktop and understand how those are working, then the advanced features don't matter much. They also get very specific to particular installations and such, so that and there's lots of documentation out there for ParaView on how to do that. And we want to leave a lot of time at the end for question and answer. And so if you are following along out there, these are some good pages to look at. The ParaView homepage is paraview.org, and if you drill down to the wiki, they have lots of information there, tutorials, other examples, things from some particular good ones are the tutorials that are given at the IEEE Visualization Conference each year, along with some data sets there, so be sure to look at those. And if I did want to throw out one URL that's a nice one for visualization in general, and that's visworld.com. That's only been live for about a year now, but it takes visualization very broadly defined, and it actually incorporates things like computer graphics, rendering, computer graphics hardware, all sorts of applications in science and information visualization and so forth. So and then it has some ways to filter out just the information that you're interested in. So be sure to check that out. So basically, what is visualization? As you all know, it's a visual representation of data. It's the a picture's worth 1,000 words, so a good visualization is worth 1,000, or let's say 100,000 numbers. So, and there's definitions for anything. Broadly beyond that, any technique for creating images, diagrams, or animations to reveal information or to communicate a message. In the field, we actually talk about, we make some distinctions between, the main one is between scientific visualization, sometimes called sci-viz, and information visualization, or sometimes called info-viz. In scientific visualization, the data comes from some type of natural phenomenon, be it a molecule, the arrangement of stars in the sky, the arrangement of bones in the human body, and those things have a natural three-dimensional representation. So the techniques for scientific visualization look at how to leverage that natural three-dimensionality of the data and to help you reveal some information about it. In information visualization, you might be dealing with networks, some social data where you have networks of connections. It might result from text mining, might result from multi-dimensional data, financial data. And these are the sorts of things that have gone on for many years in mathematical and statistical computing there, all those types of plots and things that you might do. If you're probably familiar with the work of Edward Tufte, he has some really excellent books presenting some information visualization methods. But the data has no natural spatial representation, and so it's up to the researcher, the user, to pick the one that makes the most sense for them. Some people say that scientific visualization is more or less a solved problem because we have the algorithms and such, still working on some issues of scalability more broadly, but and a lot of work goes on in information visualization. That's where people are being more creative in terms of algorithms and representations. So of course we're going to focus on general purpose scientific visualization, and that's one of the strengths of ParaView. So for example, things like molecular visualization, medical visualization, geospatial astronomy, flow visualization. Some of these things can be done in ParaView. Sometimes they're left to other specialized packages, such as, say, GIS or molecular visualization. And just examples of information visualization sorts of things include things like abstract representations of timeline, tree maps. Sorry, that's so dark here for the IU folks, but that's showing directory structure and the nesting of files within folders, within other folders, and so forth. Network diagrams, they're showing connectivity between people, and innovative sorts of things like radial maps. So where might you use visualization in your scientific workflow? There's lots of possibilities. Here's a few of the more commonly referred to ones. Exploration. In early phases, you're just getting your data. You don't really know what is interesting. You're trying to develop your hypothesis, and so you're looking for trends, you're looking for outliers, interesting things to look at and to kind of guide your scientific process. Visualization can be really nice when you're trying to debug, especially some large codes and you're getting some erratic behavior. Actually visualizing the output, it might give you some type of intuition into what's going wrong. You know, quite frequently there's errors in boundary conditions when you're running in parallel codes. Confirmation, you know, does the data show me what I expect? Am I on track? You know, and sometimes just bringing up visualization every once in a while to make sure that your runs look good. Of course, for many of these things, you can also do some type of statistical analysis, some numerical, quantitative sorts of things to verify that as well. A visually guided measurement and analysis can be sort of, you know, in the middle towards the end of the pipeline. How can you visually extract the information that you want to see out of massive data sets? What are the really interesting parts that you might want to calculate in more detail or to do more detailed analysis on? And of course, presentation for colleagues, for funding agencies, for general public, trying to communicate the impact of your work. Of course, visualization comes in there. We talk about visualization having a pipeline, which basically is something like you read your data into your visualization package, you filter it, you select some subset of what you want to see, you map that to some type of geometric representation, you actually render that geometric representation into pixels, and then you might interact with it. Okay, so be aware when we're talking about ParaView, they sort of overload the term filter, so you might think of it more in that data filtering term. And the filters in ParaView can perform some traditional filtering functions, but they also have a mapping function in there where they actually, each filter within ParaView also encapsulates a mapping and some information that helps out the renderer. So you might also visualize it as this pipeline here with the dotted arrows being the interaction, and you can interact back to any point earlier in the pipeline. In fact, that data flow paradigm was at the heart of many of the early visualization applications. Some of you may have used AVS. OpenDX is an open source version of Data Explorer. I don't know how active that is anymore. Iris Explorer, newer things like VizTrails, all incorporate some type of visual display. In fact, they let the user actually connect modules they construct their pipeline visually. So again, apologies to IU folks, but what you see there is if you were to read a file, then that actually might go over to a filter and then go over to a mapper, and so you just drag boxes between like data types, and the data will actually get flow or copied through that network. And so this is a very intuitive way, a fairly intuitive way for end users to develop their own custom applications, because they best know their science, but they don't know how. They may not know how to program or do all the things necessary for a graphical program, especially. So a little more about types of data. Just briefly, you know, you are concerned about the dimensionality of your data, and since again we're talking about scientific visualization, it could be 1D, could be 2D, quite frequently 3D, and you might have a single time step or a series. The structure of that data is very important. Is it a uniform rectilinear grid, such as this, which actually would be, in a 2D case, is your image data. In a 3D case would be your volumetric data, comes out of CT scans and so forth. The coordinates are implied there. It could be a non-uniform grid, it could be a curvilinear grid, Oh, got a laser pointer there?
You can use your mouse.
Ah, I'll use my mouse. All right. And we also have our, so here the unstructured grid goes away from these rectangular cells to any sort of triangular or tetrahedral data. And polygonal data, and of course you have just unstructured points in 3 space. And continuing on in that discussion of data, is your data connected? Is there some type of, you got points in 3D space? Is there an explicit connection between them, or is there an implicit connection as there would be in image data? And what type of data do you have there? Is the data supposed to be located within the cells that you define with your coordinates, or is it located at the vertices? It's a very important distinction. And you know your code best, and so you know which one you're doing, if it's supposed to be representing that entire 3-dimensional space, or if it's a sample at a particular location. And then, of course, what kind of data do you have there? Scalar values, vector values. You can have as many values stored for that given grid, and then most tools will let you select which of those various fields, be they scalar or vector, that you want to look at. And then how do you render the stuff? You render it as points, lines, surfaces, color mapped surfaces, volumetric data, which is semi-translucent. So this is becoming much more practical with the advent of graphics cards. So there's, many of one of the examples we're going to show you goes back 6 years for us. And at the time, only the most expensive SGI systems would allow us to do the volume rendering. Now most of you can do this very well on your laptop, thanks to the advance of the graphics cards. And in the lower right there is the non-photorealistic rendering. I don't see many visualization packages that support this, but the process of illustrators rendering out very complex diagrams, especially in the area of medicine and anatomy, goes back many, many centuries. And so borrowing from some of those techniques, we can actually render out things that don't look realistic, but they convey the information. And again, that's the goal there. So I would expect that we might see a lot more with non-photorealistic rendering in visualization packages soon. And how interactive do you need to be? You need to have it real time, where we're talking 15 to 30 frames a second, or can you tolerate something less if you want to get more data? And if it's really big, you need to go into some type of batch mode. Finally, a couple of other things. What type of display are you viewing on? Your laptop, your desktop? That's great. In fact, again, the graphics cards make that very possible. If you've got 3-dimensional data, especially if it's points and lines and things, it's hard to pull the structure out. Stereoscopic displays are very nice. There's a new wave of 3D TVs that are making that a nice feature for a lab to have. So several people can gather around, view the data in 3D, and the glasses are a lot cheaper than they used to be. Not terribly more stylish, a little bit more stylish, but you still kind of look geeky. Ultra high resolution displays are everywhere. I see several of them at our endpoints around here, and this is a great way for people to collaborate and view data at at many times the resolution that they could get on their desktop. And then finally, immersive displays, which we've had for about the last 15 years, things like caves, domes, etc., which take advantage of stereoscopic plus tracking to give a correct vision or representation of the data regardless of how you move. So it also generates a very natural sort of interaction. We've got some researchers at IU who are looking at how we can adapt these general purpose tools to work in conjunction with these immersive visualization displays, so that you don't have to leave a package. Let's say if you're using ParaView on your desktop, well, that's what you want to use in one of these advanced displays as well. You don't want to have to translate out of there. And then we're going to show you these different types of interaction, but keep in mind that, again, the focus here is interactive visualization. So you're always changing parts of that pipeline by picking things, by slicing, cutting, moving, manipulating, changing representations. So those are the sorts of things that happen